Did you know that we can look at fossils and estimate how old a rock form is from? These fossils are known as index fossils and are found all over the world. Hi, in this lesson, we're going to talk about how rocks and fossils can tell us about the history of life on Earth. So, when we're looking at rocks and fossils, there's a few terms that we need to understand. One is stratigraphic sequence. So, this is looking at a sequence of rocks that provides a chronological record of a region's geological history. And again, as we go deeper through the layers of the Earth's crust, we're actually going older. So we can see things that occurred in sequence. Another one is relative dating. And this is the process of placing rocks or other geological structures into the correct chronological order. So we're not looking exactly at how old they are or what year they were formed, but are they in the correct order relative to another? This is compared to absolute dating, which is the exact time that has elapsed since an event occurred. So we want to know when in history this occurred. And the last one is going to be intrusion. So this is a body of rock that forms from the invasion of magma into a pre-existing rock formation. So an intrusion is younger than the pre-existing rock it moved into. So if we see something that bulges into a bunch of layers of sedimentary rock, and it kind of disrupts their linear appearance, we would assume that this would be an intrusion. So when we look at the formation of sedimentary rock, step one is where rivers transport sediments which contain fossils. And over time, additional layers are going to be added on top of the previously deposited sediments. And then sedimentary rock is exposed to us nowadays when the seafloor is pushed up, um, like in upward thrusting of mountains or through erosion. So if we see in the river valleys how rivers over the years have dug themselves a deep um, trench, we can see sedimentary rock in those locations, which is one of the reasons why you can often find rocks or fossils in the Red Deer River Valley, the North Saskatchewan River Valley, and the Peace River Valley, because those rivers have dug trenches into layers of sedimentary rock that contain fossils. When we're looking at relative age of um, artifacts, there are five main principles. One is the principle of uniformitarianism. So, what happened now happens in the past. So, we're going to say that in the past, layers of sedimentary rock were also deposited in order. The principle of original horizontality. So, a new layer is placed horizontally over an old layer. If there's any folds or tilts in those sedimentary rock, this is going to indicate a geological event. The principle of superposition. The layers become younger as you move to the top. So layer A under the grass is going to be the youngest layer. The principle of cross-cutting. So disruptions, such as intrusions or faults, are younger than the layers they disrupt or cut through. And then the principle of faunal succession. So layers of rock with similar fossils or rocks are, so similar fossils or similar rocks are of the same relative ages. And the age in terms of older or younger, and in terms of older than or younger than. So we know that, and also fossils that lived for only a short period of time are good and are known for the age of that rock, are known as index fossils. So if we have a fossil that was known to exist only in a short period of time, and we found it in Alberta, and we found the same fossil in Mongolia, we can assume that those rock depositions are roughly the same age. And so it allows us to then compare the fossils above or below it. The geological time periods are separated into three main units. We have eras, which are large units of time determined by global events or geological changes, and there are four main geological eras: the Precambrian era, the Paleozoic era, the Mesozoic era, and the Cenozoic era. Then we have periods, which are units of time within each era symbolized by regional changes. And finally, we have epochs, which are the smallest units of time within the Cenozoic era, which are based upon the rise and fall of the sea levels. So this image is in your data booklet. So the Earth's time is divided into four eras: the Precambrian, Mesozoic, Cenozoic, and Paleozoic. And there were massive disappearances of fossils and appearances of new fossils between each one. So the Precambrian is at the bottom, Paleozoic in the second from the bottom, Mesozoic, and then Cenozoic at the top. But if you look at the millions of years ago, this is not made to scale because the Cenozoic is the shortest time period between 65 and 1.7 million years ago, where the Precambrian was from 4,500 years ago to 590. So it would take up most of the time period of the Earth's history. So the Cenozoic era began with the extinction of non-avian or non-flying dinosaurs to the present. And it's called the age of mammals, flowering plants, insects, fish, and birds. And it's divided into two periods. The Quaternary period, which is the present, and there's two epochs within that Quaternary period. The Holocene epoch, which we're currently in, and the Pleistocene epoch. So that's the most current period. And then the other period that it's divided into is the Tertiary period. And the Tertiary period was when the Cypress Hills were formed. And there's resistance to erosion of the rocks found in the surface of the Cypress Hills. So this happened in the Tertiary period. In the Mesozoic era, dinosaurs were alive, and it was a time of great change in the terrestrial vegetation. Mesozoic era means middle animals. So we had land animals, but before there was mammals. The Mesozoic era is divided into three different periods: the Cretaceous, the Jurassic, and the Triassic. So during the Cretaceous period, we had different depositions formed, known as the Edmonton Group and the Bearspaw Formation, as well as the Crow's Nest volcanics occurred here, the Catamount Formation, and the Kootenai Formation in the Rocky Mountains. In the Paleozoic era, multicelled animals underwent a dramatic explosion in diversity. So this was after the Precambrian era. The 6 continents experienced mountain building, and the Paleozoic era ended with the largest mass extinction in history, and it wiped out about 90% of all the marine animal species. The Paleozoic era is divided into 6 periods: the Permian, the Carboniferous, the Devonian, the Silurian, the Ordovian, and the Cambrian. So the Cambrian's oldest. We'll often talk about the Cambrian explosion. And this is where there's a lot of fossils found from the Cambrian explosion in Castle Mountain, as well as in the Burgess Shale in Yoho National Park. The oldest era is the Precambrian era, which makes up roughly 7/8 of the Earth's history. The Earth formed, life arose, tectonic plates moved, cyanobacteria evolved. This is where we see the first evidence of oxygen, and the first animals evolved. So here is a different vision of a timeline of the history of the Earth. And so we can see in blue here the Cenozoic era with the Quaternary period at the very top, where we currently are existed, followed by the Tertiary period, the Mesozoic era in the yellows and oranges, and the Paleozoic era in green, followed by the predominant amount of time of the Earth's history, which is the Precambrian era, where life originally formed. Now, looking back at the law of superposition, this is when higher strata, higher layers in the sequence of rocks, are younger than lower strata or lower layers of rocks. So when we're using fossil dating, do we use absolute or relative fossil dating? Well, first we use relative dating to place these rocks in order. And so if we're using relative fossil dating, we would be using the law of superposition. So here is a quick practice problem using the law of superposition. So the following drawings represent the steps in order to make tungstone. Put them in order from the first to the last. Okay, so one of the things we want to do is identify different layers of rock. So one of the ones that I'm going to identify, because it's easy for me, is this kind of brown layer here. Okay, and we're actually going to be seeing the fossil of that shark. So this would be step 1. Okay, now this here is going to be step 2 because we have only one layer above that kind of brown and yellow. Here the brown and yellow is covered by 3, so there's going to be step 3. Okay, now here's that brown and yellow, and this one's going to be step 4 because we have one more layer over top of it. Now looking at the last ones, this is going to be step 5 because we have these layers, and there's our fossil as well, but it's not exposed yet. And then lastly, this is going to be step 6. There's that layer that we looked at from the beginning, and there's our fossil, but it's now exposed so that we know it has to come after step 5. So we can put those in order relatively by looking at the different layers above the sediment. So looking at these pictures again, we're going to look at how fossilized shark teeth become embedded in rock high above sea level. So that shark living in an ancient ocean sheds its teeth. The teeth sink to the bottom of the ocean and are buried in a sediment. So as sediment falls from the top, it ends up burying those teeth. Over time, the sediment hardens and becomes sedimentary rock. Over more and more and more time, more layers are deposited, the sea level drops, and those layers become lifted, and the layers are, so the ocean either drops or the layers become lifted to become dry land. Erosion happens, creating an outcropping, exposing the layers of rock. So this can either happen through upthrusting and like mountain formation, or water erosion, creating like a river valley. And then the site would be excavated to expose the fossils. So we can see, based on the different layers, how old or how the relative age of the fossils, and then through geological processes, those fossils are visible. So what can be fossilized? So anything that is hard matter, which would include shells, teeth, bones, corals, and even diatoms. So any of these can become fossilized. So how do things become fossilized? The one process involves an item being buried, especially somewhere where there's lots of minerals. So usually in a water source that this happens. Then over many years, the minerals are going to seep into the pores of the hard parts. So they'll go into the hard part of the bone, the hard part of the teeth, the hard part of the shell, which over time is going to replace the hard part of the organism to create a mineralized form. So when we look at fossils, they're not actually bones, they're very heavy because they are complete mineralized bone. Another process by which fossils are created is going to be an item being buried, and then it's going to be compressed into the rock layers beneath it. And then over time, as that organism decays, it's left behind an impression of itself in that where it originally was between those rock layers. So looking at relative aging and fossils, scientist William Smith observed that certain fossils kept reappearing at each surveyed location. So there were some distinctive fossils that occurred at location 1 and location 2 in layers of rock. And these fossils always appeared in the same order within layers of rock. So, if a distinctive fossil only existed for a short period of time, then the rocks containing that fossil must correspond closely in age to other rocks that contain the same fossil. And these fossils are known as index fossils because they establish a common time of origin for widely dispersed rock layers. So they're known as index fossils because we can index how old rock layers are. So if we look at these two rock layers, we can have rock layer Y is going to be the same relative age as rock layer R at this location because they contain the same index fossil. So a fossil used to determine the relative age of a layer in a stratigraphic sequence, or it matches stratigraphic sequences from different locations. So if we find an index fossil, we can relatively age that layer, or we can compare two different sites. Typically, index fossils are better preserved fossils from a very short-lived species that's known to have existed during a specific time period, so that we can easily date that rock and it has a short time period as opposed to a really long time period. So scientists are going to use different processes of dating to put a particular age to a fossil, and then when they come across that index fossil, no matter where in the world, we know the approximate relative age of that layer. So determine the oldest layer of rock at location 1 and 2. Okay. So the oldest layer of rock at location 1 and 2 is going to be, the oldest layer of rock at location 1 is going to be rock layer S, and at location 2 is going to be Z because they're at the bottom. Youngest rock at location 1 is going to be P, because it's at the top, and location 2 is going to be W. Now we're going to conclude which layer in location 1 contains a rock of what layer X of location 2. So layer X contains that shell fossil, and it's going to be roughly the same age as layer Q at location 1. Okay. So we can compare the relative age of those locations. So graptolite, placoderm, and ammonite are the most suitable index fossils because they're only found during a short period of time. So again, they have to appear only briefly in the geological record, have a wide geographical distribution so that we can date rock layers around the world, and be easily recognizable. So we don't want it to be a very complex fossil that is similar to other fossils. We want this to be easily recognizable once it's found. So fossils are not just important for geological dating, but they also form the primary fuel we rely on in Alberta. So geologists suspect most of Alberta became submerged at the bottom of a tropical sea by the end of the Ordovician period. Over the next 200 million years, sea levels rose and fell. But when it was submerged, Alberta became home to a now extinct group of sponges. Now, these sponges secreted a brittle calcium carbonate skeleton that, together with the coral, became the component for reefs that occupied hundreds of square kilometers of the underwater environment. Now, these reefs, which could have been up to 10 stories tall, became the storage containers for life that would later form our petroleum reserves. So our natural gas and oil was formed in these giant underwater reefs. And so this happened in the Ordovian, the Silurian, and Devonian periods. So over the next 200 million years, these microscopic organisms, mainly plankton, were living and dying in the warm tropical seas that covered Alberta. And geologists suspect that the dead plankton covered thick blankets of, as they died, they covered the ocean floor with thick blankets of organic ooze, and then became a food source for bacteria. The bacteria were thought to have removed most of the oxygen and nitrogen from the organic matter for their chemiosmosis, and this left behind carbon and hydrogen, which are the main ingredients in petroleum. Then, during the next 380 million years, this layer of organic material was subject to heat and pressure that encouraged chemical reactions to occur, and thousands of meters of sediment were piled on top, and that sediment on top was eventually changed into rock. Once those hydrocarbons had been converted into liquids, the pressure from above pushed these materials into more porous rock, so the fossilized remains of the ancient reefs. So we have this thick layer of ooze that was then turned into hydrogen and carbon, and it was buried under further and further layers of sediments, eventually pushed into porous rock. Now, since the rock type above and below the reservoir of petroleum was impermeable, that petroleum had no place to go. So a large concentration of petroleum in subsurface rock is called a petroleum trap. So the petroleum was trapped above an impermeable rock layer and below another impermeable rock layer, so it had nowhere else to go. And so this happened under Alberta, well, on the surface of Alberta, but now it's many thousands of meters under the surface, which is why we have to drill and mine to get to it. So in chapter 2, we were introduced to 3 fossils, a trilobite, a conida, and a hallucigena. And all 3 fossils have been found at the shale on the side of Mount Wapta, about 80 kilometers west of Banff and Yoho National Park. And this location is known as the Burgess Shale, and it's one of the most important sources of Cambrian fossils on Earth. It's actually a UNESCO World Heritage Site. And geologists have evidence that more than 500 million years ago, the organisms now fossilized in the Burgess Shale were inhabiting a shallow area close to the shore of a tropical sea, so like a reef area. So here's an image of the Burgess Shale. And the Cambrian age rock found on the side of the Burgess Shale it has well-preserved fossils. They're right on the surface of the mountain. And if you so desire, there is an opportunity for you to join scientists and go for a hike up to the Burgess Shale. But because fossils are part of the public record, it's something that you aren't allowed to keep or take with you. So maybe that's something that you guys will do one day.